please. Piano, please.
Do you believe you live on a globe?
Yes. Yeah.
Yes, I do. You do. Can I ask you why?
Because there's images from space that make the world. There's enough scientific proof to prove that we do.
The same as these two guys. Scientific proof.
Could you give me your best proof that you live on a globe?
I'd have to Google some sort of image of the world, but that's as good as it comes.
So would it be true to say that you believe it's a globe because you were taught that?
Yeah, that'd be accurate. Yeah.
That's accurate. What about yourself?
Tim Peake's Twitter account.
So you
believe,
believe
yeah.
Tim Peake yourself?
But I believe in all the science, but also all of the images that we've seen of the Earth from space.
So I'll go back to those in a wee second,
Decades.
right? So I'll declare me just before we start. I follow and I study natural science. Are you aware what natural science is?
Do you think so?
Natural science, you have formal science and social science. Things like mathematics are a formal science because they don't depend on empirical observations. You can start from an axiom or a presumption, you can create a mathematical model. You understand these types of things?
Yeah.
So natural science for me is observable, testable, repeatable. Would you agree that that's the core of science?
Yeah.
So if I make a claim to you about reality, I should be able to scale it, produce it, repeat it, and everybody can then do that. Would you agree?
Yeah.
Would you agree?
Now, if you have a claim that can't be tested, that's what we call pseudoscience. The difference between pseudoscience and regular science is whether or not you can test it.
So, could you give me one practical example of a body of water conforming to the exterior of a shape?
Off the top of my head, no. I don't think so.
No, you couldn't. Can I ask you why you think that's not possible?
Not sure. I failed science, so I've got no idea.
I'm struggling as well, I'm afraid.
See, one of the big ideas in science is that an experiment can be repeated. Someone else can do the same thing and get the same result.
If I says to you, if I wanted to establish level with something, I would use water to do that.
Correct.
Would you agree with that?
I would agree with that.
Why would you agree with that?
Because it's tried and tested for thousands of years.
So if I says to you that a body of water, it's always going to find its level,
Find its level.
and the surface is always going to be parallel.
It's fluid mechanics, is it not?
Fluid mechanics, aye. So these things to me are applied and they're tested and they're known and we use them every single day.
Yes.
But yeah, I'll come right to the crux of the matter. People are trying to tell me that the world's a round ball. That's 80% covered in water.
Okay.
You're a tradesman and I'm a practical guy as well. And I mean, I'm looking there.
You're looking at that body of water.
I'm looking at a contained level body of water. Right? But yet they're trying to tell us that the Earth's a round ball. Do you believe that it is a round ball?
I believe it's a round ball.
You believe it's a round
yes,
ball?
I do as well, aye.
Can I ask you why?
I'm not going to say because I was told so.
Well, that's an honest answer and that's pretty much the same as the rest of us. I believed
I
it.
couldn't explain the science behind it, but I'm prepared to go along with that science, you know.
But just as we said a minute ago, based things on substance, practicality. If I test water and I can go out and I can take any bit of that water and test it, I can say that bodies of water have not got the ability to display convexity or conform to the exterior of shapes.
But surely gravity plays a big part in that, does it no?
Well, you know, you'd have to define gravity and then, you know, practically prove it, but yet the
Well,
main...
gravity, definition of it really is a force that is exerted by mass, is it not?
Well-
If anything has mass, then it exerts gravity.
Yeah.
So that, for instance, your cycle helmet here is actually exerting gravity on the Earth. It's pulling it towards it. Well, it's such microscopic levels that actually there's larger mass in the Earth, so it's pulling.
But what if I says to you they've never ever proven that?
Well, I haven't proven it. I'm not a mathematician, but I know that mathematicians have proven that it does exist.
But mathematics is a language, it's a formal science. And like any other language, you can start from, you know, but mathematics can start from an axiom, an assumption, and it can build a mathematical construct that works mathematically on paper. But in order for it to come into natural science, like substance, it has to match practical reality. So they can tell me mathematical equations about how oceans are wrapped around a ball, but in practical reality, water doesn't behave like that.
What is gravity?
You have no idea. Okay, next question.
Wow.
No, here's the difference. We can describe gravity. We can say what it does to other things. We can measure it, predict with it. But when you start asking, like, what it is, I don't know.
It's no use you presenting the
That's
theory
the
on my
world you
table.
work in, isn't
That's
it?
the world you work
Yeah,
in,
of
you're a
course.
lawyer. And if I come to you and say, here's my theory, you are then going to say, please back this up with evidence.
Evidence isn't proof. Evidence acts towards proof. If it's proven to be correct, then yeah, evidence becomes proof.
The gravity thing is, they go, it's a theory, and then people go, where's the proof? Oh, well, it's keeping you to the floor. Oh, okay. But you don't see gravity, you don't know where it comes from. There's no gravitational waves. There's, you know, we've got this other option of buoyancy density. I'm heavy.
That makes sense.
Well,
It's a kind
it's a kind of magic.
That's the gravity.
You know,
That's what we say.
scientists are like the new religious wizards who they've got a white coat on, whatever they say, oh, it must be right. Let's get on with our lives. Consuming, watches. Scientist comes on the telly, Neil deGrasse Tyson, whoever, whatever he says, we swallow the new priests of the new age.
If you have a claim that can't be tested, that's what we call pseudoscience.
So according to Neil, this is called gravity.
This is called gravity.
But when you ask Neil what gravity is, he doesn't know. He doesn't know what it is. He just knows what it's called.
But when you start asking, like, what it is, I don't know.
Right? So let me ask you this, Neil. What is this called? How come that didn't drop? What's that called? What is this called, Neil? Is that called anti-gravity? Is that what it's called? I'm not gonna ask you if it is anti-gravity because you don't even know what gravity is. Apparently, a super scientist such as yourself and professional actor, you're only qualified to tell us what gravity is called. You're not qualified to tell us what it is. So again, Neely boy, how come I can't drop this helium balloon even when I try? Why is it rising?
Imagine this. Whenever a boat's in the water, it pushes some water out of the way. We say it displaces some water. See, displace, place away, you with me? So it's as though this model boat of science were making a hole in the water shaped like this. Now take a look. This is the aquarium of science, and it's filled right to the brim. As the boat settles in, it displaces some water. It runs over the rim, down this gutter, into this pitcher. Now, the model boat of science displaced this water. In fact, all boats displace water. In fact, everything you put in the water displaces some water. Hot air balloons float. That's right, they have buoyancy. They're just like a boat or a buoy, but they're floating in air instead of water. Now this is our hot air balloon trash bag of science, and I'm going to inflate it using this hairdryer. Hot air molecules are moving faster than cool air molecules, so you need fewer of them to get the balloon to hold its shape. So it weighs less, it displaces the cool air around it, and it has buoyancy. It floats. If you can displace enough air, you'll go up, just like a bubble in water. A hot air balloon is like a bubble in air. It's buoyancy! We're floating!
Allow me to explain what density and buoyancy is. This microphone is more dense than the air in which surrounds it. It's made of plastic, metal components, and the plastic and metal components of this microphone are more heavy than the air in which surrounds it. So therefore, when I drop it falls. No gravity, no attraction towards the theoretical center of the earth. No, no, no. This microphone is more dense than the air in which surrounds it. It won't fall until I pick it up and release it. When I choose to release it, it indeed does fall. Not because of gravity, but because the microphone is more dense than the air than which surrounds it. Now, on the flip side, what causes this to rise? Is this a case of anti-gravity, folks? Oh, no, no, no. This is a case of buoyancy. You see, there's helium inside this balloon. And even when I try to throw it down, it rises. How can the helium in this balloon overcome the force of gravity, which holds trillions of gallons of water stuck to a spinning ball? How can this helium rise and overpower the balloon? That's because the helium is less dense than the air in which surrounds it. So therefore, because of buoyancy, it rises. Yes, folks, there is no gravity and there is no anti-gravity. There is only density and buoyancy. Here it is once again, folks. Density and buoyancy. Density, buoyancy. 1, 2, 3. There you go, folks. Density and buoyancy. The microphone falls because it's more dense than the air in which surrounds it. The helium balloon rises because the helium in the balloon is less dense than the air in which surrounds it. Density, buoyancy, density, buoyancy. There is no gravity, only density and buoyancy.
If you can displace enough air, you'll go up. Just like a bubble in water. A hot air balloon is like a bubble in air. It's buoyancy! We're floating!
In natural science, testable, observable, repeatable 100% of the time. Two opposing pressure systems require a solid separation between them, or else we have a thing called equilibrium. Do you understand what that means?
Yeah.
Yep. So, you know, a vacuum, which is a negative pressure system, and a positive pressure system is what we live in. Do you think that the two of them can exist side by side without a solid barrier?
It's a good question.
Would you have a practical example if you thought it was real?
No.
Right?
I don't have any examples. I don't think so.
So if you took a deodorant can out and removed the metal, you know, and you just had the gas there, would the gas keep its form, or would it equilibrate with the rest of the...
Equilibrate.
Because that's what we know in the test and the reality 100%. They say they're going up into this vacuum of space, right? So for me, we live in a pressurised gaseous environment, and they're saying that's a vacuum. Well, there's no solid barrier between them. Yet we go to physics and everyday practicality again. I'm sure you'll concur here. In order to have two opposing pressure systems next to each other, you need to seal them. Would you know, or they would equilibrate?
We need to seal them.
They would have to be separated from each other, would they not?
Aye.
And that's 100% everyday experience, practical reality. So that's for me science, but yet you've got these institutions trying to tell me that on a bigger scale it behaves differently, when I don't have anything practical to make me believe that. So if they were saying there's another medium up there would have to be something solid separating them. I mean, again, you know, if they're saying they're going up there and it's a vacuum, you know, that doesn't make sense to me. So, and again, you couple that with the fact that there's no real photographs and real videos, it tells me that they're doing it in Hollywood studios. I mean, if I go to something else, you know what the horizon is? What shape's it?
Slightly curved, I believe, to follow the curvature of the Earth.
Well, it's called the horizon, it's not called the curve horizon. It's a horizontal.
Level plane.
Level plane.
It's a level plane, but I think.
So would you refuse to trust your senses and what you observe based on? I mean, if I
would use the horizon as my level. If I look across there, well, we meet the Isle of Bute. I can kind of roughly gauge above sea level with the contour of that, the Isle of Bute there.
Yeah.
And I'm using the horizon. Well, I'm using the sort of sea level to gauge that.
So you said
I'm using my eye there.
But you said another thing there. You said sea level.
Sea level.
What does that mean? How can you have sea level on a bar?
So,
if we judge landmass,
we're getting back to the
point.
If we lived in a globe, do you think it would be easy to prove?
If you'd studied it for your full life, probably.
Why your full life?
I don't know, because you've made it sound like it's something that's hard to prove. So.
Well, you know, have you ever experienced curvature anywhere?
I don't think so.
Yes, I have.
Where?
I've spent quite a lot of time on ships,
Where have you seen the curvature?
Well, not actually seen it, but I'm trying to remember the best way to describe it.
Yep.
But you can see when you're out at sea, especially with the sun going down, and the higher up you go, you can basically describing this really awfully. Sorry.
Can I help you?
Yeah.
Can I help you? Because this is a thing it's a perspective issue.
Yeah.
How our eyes work, right?
Yeah.
We have a horizon. You know what a horizon is? You know, the horizon's always flat and parallel, and it will always be at your eye level, no matter how high you go.
Yeah.
Okay. Well, we have an issue when we're looking over a long distance because of how our eyes work. Now, if you can agree or disagree, when we look into the distance, the floor rises, the sky comes down, and the sides come in. So if we're looking along a train track, the train track, you can see the width while you're standing. As you look along the train track, it starts to narrow, come in on itself. That's how our eyes work. Now we have a thing called the vanishing point, convergence, where things condense so much they become so small that they vanish. Now you'll have heard, I'm sure, in your lifetime that ships disappear over the curvature of the Earth. Am I correct?
Yeah.
Yep. Yep.
Take a look at this. It's our curvature of the Earth horizon model of science. And this blue stuff is like the ocean. And this boat,
Well, it's like a boat.
anyway. Watch. As ships sail away.
They don't disappear all at once.
No, first, the bottom will disappear. See, the bottom of the ship is gone. Now we can see midway up, and then the whole thing disappears.
Now you're aware nowadays that we have technology like super zoom cameras. There's one in particular called a P900 Coolpix. We can observe a ship going into the horizon and totally vanishing, totally gone. We can then pull out the camera and zoom back in and bring the full thing into full view again. Okay? Another contradiction with what they're telling you is that they say that happens between 3 and 12 miles, straight out in front of you, okay? Now we can have an unobstructed view from left to right up to 100 miles, absolutely zero curvature. Do you think that's a contradiction?
Most likely, yes.
I think so. I'm not sure.
Well, if I says this to you, if you were saying to me that straight in front of me something was going over a curve, but I had no curve from left to right up to 100 miles, that would tell me that I was living on a cylinder. Would you agree?
It could be seen like that, yes.
Presume so. Yeah.
It's a pretty simple question. What's the shape of the thing that we're standing on?
Now, for such a very simple question, we don't get a very simple answer. In fact, we get many, many different answers. Here is some of the answers we get to this question from people all over the world. This answer comes in from K. Carl Manley. Imbecile! If you go to the beach on a clear day and look out over the ocean, you can see the curvature of the earth. But anyone can talk, and I'm hoping I have enough sense to never ever pay any attention to religious fools with their literal interpretation, i.e. firmament again. The rest of you followers should consider that the NWO order wasn't satisfied dumbing down the video watching generation. They had to trick them into embarrassing themselves with their stupidity by sparking this quote-unquote debate. Oh. Okay, well thank you for that, K. Carl Manley. So apparently all you have to do is go to the beach on a clear day and you can see the curvature. Well, here's a differing answer, and this comes in from John Bauer. I asked John Bauer, so what height do you think it should start to be visible? And John said, I'd say about 500 feet. The higher you get, the more prominent the curve gets. Oh, well, that's very interesting. Let's see what Fisher of Men has to say about this.
Here's a photo from a very high mountain overviewing the valley below. And what you see here is the curvature of the Earth. I myself have been on a very high mountain like this, and I've seen the curvature of the Earth, and I told myself, wow, I can see the curvature of the Earth from here.
Well, thanks, Fish. Next, we'll hear what Maxim Beatty has to say about seeing the curvature of the Earth.
Genius, what about the images I see with my own naked eyes when I'm on a plane? Sometimes when I'm on a plane, I can see the Earth's curvature from the plane.
Okay, so as you can see, I get a range of different answers to this question. Go to the beach and you can see it on a clear day. You can see it at 500 feet. You can see it out the window of an airplane. That's usually when my go-to rebuttal is, hey, how come whenever we send up a high-altitude balloon with a camera attached to it, they'll even go up as much as 20 miles high at their peak, which is well over 100,000 feet, how come we still see a flat level horizon? But as I've shown, many ball Earth believers will tell you that they've seen curvature from a range of different distances. However, when I break out the trusty old balloon footage, then they certainly change their tune, and then they want to turn around and tell me, hey, you're not high enough to see the curvature.
It's a fundamental fact of calculus and non-Euclidean geometry. Small sections of large curved surfaces will always look flat to little creatures that crawl upon it.
In fact, just listen to Steve Little. He says the Earth is pretty large. You need to be a lot higher up. I said, it goes up over 20 miles high at its peak. That's over 100,000 feet. Please tell me at what altitude is the curvature of the Earth visible? To which Steve Little replied, try 200,000. But what do we know? We're all just a bunch of regular know-nothings. Why don't we ask a world-renowned super scientist like Neil deGrasse Tyson? Hey Neil, tell us about the curvature of the Earth.
The Earth looks flat because, one, you're not far enough away at your size. Two, your size isn't large enough relative to Earth to notice any curvature at all.
Bill Nye the Science Guy.
Watch. As ships sail away. They don't disappear all at once.
Science rules.
First, the bottom will disappear. See, the bottom of the ship is
a property of matter.
Now we can see midway up, and then the whole thing disappears.
T minus 7 seconds.
So it's not enough to be 100,000. You gotta try 200,000 now. So which is it, people? Can we see the curve, or can't we see the curve? This is getting ridiculous. You can't have it both ways. If I prove to you that there is no curve at 100,000 feet, then you turn around and say try 200,000? What about all your ball believer buddies who just told you they saw it from the ground, or on top of their house, or on a hill, or on a mountain, or from a plane's window? You guys need to get your shit straight.
In the heliocentric model, we are told that the Earth is an oblate spheroid, or an irregular geoid, roughly 25,000 miles at its circumference. The Earth is rotating at roughly 1 an hour at its equator and is circling around the Sun at a distance of about 93 million miles away. And all of these things are considered absolute facts by modern science. The curvature formula for the Earth is as follows. So, for instance, your curvature drop in 1 mile will be 8 inches, but if you take it out to 9 miles, it would be 9 squared, or 9 times 9 equals 81, and then you would take that 81 times the 8 inches, making the curvature drop equal to about 648 inches, or roughly 54 feet at 9 miles.
So first and foremost, I'm just going to show the destinations, the distances, the elevations, and I'm going to show the elevations of the land masses that we are looking at. First destination is here, just at this point here, okay, and as I pointed out before again, just going to have a wee scroll through here. Different day, Ailsa Rock clearly visible. The elevation of that point and the height of the camera on the Google mapping van is not going to be that much different. You know, we were here, so the tripod had an elevation of 2 feet. So that's the first destination. Here. So we're seeing here the bottom 1.2 meters or 3.9 feet. So we'll add the 2 feet of the height of the tripod and the camera, so 6 feet. There we are, 62.66 this time, so it's kilometres, so 38.9 miles. So you can see here where we are. Get it?
Yeah.
Now, there is the rock. Now the important thing to notice here is this reflection here, people. Okay? Hugely significant, hugely important. You're seeing the reflection of the rock because the water is continuing all the way, but because of this band, the optical effect that we don't have an exacting science for here, because our vision is limited and the sky is being reflected on the water, right? Same as the rock is being reflected on the water. So we can see up to this point, which would be our horizon, and then beyond that we're having serious problems. I mean, you can see other objects here in this band, right? But the important thing is the contours of the rock and the reflection on the bottom of it. Now, that rock is only 1,100 feet in height, so the calculation for that distance was 800 odd feet. So really you should be seeing about that much. The obstruction should be away up here, right? And that is beyond. So you're not looking beyond a curve where the rock is being refracted up into your visual range, horizontal, perfect for you, and displaying a reflection. Okay? Solids display reflections. Mirages and imaginary invisible stuffs do not. So the huge significant aspect to that is the reflection that you're seeing on the water that's leading all the way up to it. Alright? So that's the first observation from Largs to Ailsa Rock.
Right now I think we must be a bit more actually.
The second destination is here. So this is where we part. and we walked down onto the beach here. So we're looking here at the rock again, and also the peninsula here that you're going to see in the observations, which reaches out to Stranraer. So that furthest point that we're seeing there is 75.5 kilometres, miles 46.9. So we're seeing a generous 8 feet to this, although it's no. Right, there we go. We're at 8 feet, 46.9, 1200 feet curvature. Right. And I'm going to come across to the landmass here, and I'm just going to randomly dot it. So that first one is saying it's a height of 125 feet, 317 feet, 682, 777, 500, 400, 337, 605, 703, 480, 700, 770, 700 again. Right, there's a maximum point there of 1455 feet. So the curvature is 1200, it should be missing, so we should really be seeing the tip of this highest point here, and that is about all. Okay, so huge distances. I think I've covered the location and the distance and the elevations, so let's now go to the footage. So this is the second destination. You can see how low down we are here, right? But I was generous and gave it 8 feet. So we can see the rock here, but this observation is not the one I'm wanting people to focus on. It's when we cut across to the peninsula. Again, you can see the reflection here. Here's the important parts as well. So remember the elevations I showed of this whole area up to this far point, and the highest being 1400 feet, which is all you should see. I mean, here you're seeing the wind farms. So if I just go back to before we scan it. You can see the landmass here, stretching all the way across. Remember, you shouldn't be seeing any of this. Highest point here somewhere or here, but we're saying 1400 feet is all you should see. You shouldn't be seeing any of this. Absolutely none of it. Okay, it should be gone. Right. Now, I don't want to keep going over and over on it, people. As I said, you know, first and foremost, see this stuff here. This substance that's abundant on Earth that we know and that we can test its physical properties and its behaviours, and everybody can do so. We know that from this landmass to that landmass, this substance in between here is at the same elevation. It levels out. The substance does not have the capabilities to hold itself and display convexity upon its surface. It is level from here to here, from here to here, and from here to any other landmass that's way beyond. The body of water is level. That is a fact, fundamental fact. The optics are always going to have to play a role It is something that we did not have an exacting science for, but what you can, take from this is that none of this should be visible. The rock from Largs, you should only be able to see the top 150 feet of. When you cannot, you can see the whole thing and you can see it reflecting in the water underneath it. There is no excuses that anybody can come up with, right? No amount of equations and wishful thinking is ever going to change the fact that the substance from there to there is level, and that we are actually seeing things that are actually there. And the tens of thousands of people who live all along this coastal route see these things just about every single day, and in the right conditions they can see all the way across the island. So let's have a wee look at Google Maps. So we're talking about here. We'll go to the closest point. Just about 100 kilometres, right? So nobody should be seeing any of that. That should be way gone on your imaginary ball. All this blue stuff here, I suggest that you understand this substance that's here, this abundant substance that from each point to other point of landmass is level from one point to the other. That's its behaviour. And you are so tiny in comparison to these vast distances. You are being obscured by all sorts of atmospheric conditions and limited perspective.
Here's an interesting video I saw online regarding a full day time lapse. Now, this is quite extraordinary, actually. This is from skunkbayweather.com, September 7th, 2012. Notice the buildings and the shoreline here over on the left. Keep your eye on that. Just watch that, and the mountain in the background. Everything's pretty cool. You can see pretty much everything there, but as the day progresses, and we are now at 9:30 a.m. and it's 59 degrees, 60 degrees, it's getting warmer, the temperature is changing, we start to see some miraging take place, right? It starts to distort things a little bit. Ooh, look at that. The water seems like it's getting higher, and we're losing buildings, and we're losing the beach. Here it is now, noon. 63 degrees and climbing. Uh-oh. There it goes. Oh, there it is again. Oh, it's all miraged. Huh. It's all distorted. Sometimes you see it, sometimes you don't. The default is to see it, though. And that's the point. The default is minus distorting atmospheric conditions. You would be able to see everything clearly. But due to different temperature variations and density in the atmosphere and whatnot, sometimes you can see the whole shoreline and the buildings, sometimes you can't. But the magic trick is not in being able to see it, it's what is taking place that obscures your ability to do so. Look at this. And the mountains in the background shrink and expand and everything too. I would suggest that you hit pause on this video and rewind and watch that back and forth a few times. Look at the comparison right here, just in these two images right here. The one on the right at 5:44 p.m., 63.5 degrees Fahrenheit. Can't really see anything on the left shoreline there. And on the left at 9:43 a.m., when it was 59.5 degrees Fahrenheit, we can see the shoreline, we can see buildings, trees, all kinds of stuff. So, I mean, either this lake is, filling up and draining so that the water level is higher or lower, or it's due to atmospheric lensing and distortions, refraction, and all that good stuff, causing us to not be able to see at a certain time.
Now I'm going to stand back and just show you where my camera's at. This is where I normally film from. There's this little path, and there's the boardwalk that they put out here. again, you know, I'm saying that the water's actually even up higher, you know, and you see the mirroring going on underneath that rack. Of course, it's distorted. It looks like a mirage, but there's no magical force pulling that up. You can see birds land on the damn thing, for crying out loud. As I zoom back, you know, you can see the layers of clouds. And there's always that little gray spot in there that I like to call the gray area, because that's where I think that convergence is at. And again, look at the mirroring that occurs on this. Okay, see the mirroring of those bird racks? And what's cool is seeing the birds. The birds give it away. It shows you that they can be in mid-flight and they'll disappear underneath that mirroring area. And that's why I say that's what cuts off buildings and objects, is that mirroring effect that occurs. It's an illusion. And there's a is that Bill Watts rack right there. Zoom in on it and see how it's being affected there. Hopefully we can catch one of these birds or something. Okay, here we go. Okay, I'm back down here at Bayport again. There's the deck. There's my camera. And look how much farther in the water is. Okay, I'm just gonna let it sit there, show you. And what I'm curious of is if I can find that other bird rack that I tried to find this morning. And what I'm curious of is if I can find that other bird rack that I tried to find this morning. No, shit, there's the bird rack. Look at that. And then there's one to the right of this one too. Look at that. That's even further back. Holy crap. There's the sign. Huh. So tell me, how am I seeing that? I couldn't see it this morning because of the light refraction, but here I can see it now. It even looks like a boat or a canoe or something sitting out there. He's just doing some flats fishing or something. just sitting in the water. All that reflection. See if I can find this other. The shrimp boat coming in.
Here's a good question. How high does one have to ascend in height in order to actually see curvature? Like, there's got to be a mathematical formula for that. I mean, this is a good question. So if one's line of sight maintains focus at the horizon at all times, and we ascend and climb straight up, higher and higher and higher, how many miles up is it before we start seeing the actual curvature of the Earth and into deep space, if you will? I mean, this should be, from my understanding, a mathematical constant, probably an exponentiating mathematical constant at that. And yet again, if the Earth is spherical, and help me understand this, shouldn't there be yet another general mathematical constant as to how far away the horizon will be? So if you're standing at sea level for, say, a 6-foot tall person, that's not me, 6-foot tall person standing at the sea level, should the horizon not be, generally speaking, a set distance away? If your line of sight is on the horizon at the whole time and the Earth is curved, that horizon line should be, in general, generally speaking, a set distance away. That should be a mathematical constant. That seems very reasonable to me. The first one is from YouTuber Jenna Freda, and it's an incredible video of Jenna zooming her camera across a lake at a distance of over 30 miles. And as you can clearly see right here, you can see almost the entirety of the city with just a bit of the street obscured from view. And then she shows a shot at the end of the video of the city skyline and then a screenshot from her video. And they look pretty damn close. Almost identical. And then ODD shows another video of an independent balloon launch using a camera with no fisheye lens, so there's no distortion in the lens. And this balloon reaches elevations of over 121,000 feet, which is nearly 23 miles. And as we can clearly see, not an ounce of curvature is to be found. We see neither curvature left to right, nor descending away from us. We see none at all. You know, it would be really great to get responses about this singular question of curvature that doesn't rely on ad hominem attacks or misdirections or calling people stupid or anything of the like. I would just love to focus on this one question. Can we measure curvature? Seems pretty simple. I don't want to hear about globe heads and flat tards. I don't want to hear about how dropping a mic on TV somehow proves gravity, or how the southern star rotations don't work on a flat earth model, bro. I don't want to hear about how the sun can't possibly be 93 million miles away, or dude, the lunar eclipses don't work on a flat earth, idiot. I don't want to hear about how there are no satellites, or how Google Earth proves the sphere, or how Google Earth proves the flat earth, or what about the Coriolis effect, or how Eric Dubé is a secret agent working for the CIA infiltrating the truth community, or how Aristophanes proved this shit a few thousand years ago, dude. I don't want to talk about any of that. I want to focus on one question. Does the Earth below our feet have the curvature that we're told it has? Because if it doesn't, then the entirety of the science attributed to it falls flat, if you will.
Why do you think that Truman has never come close to discovering the true nature of his world until now?
We accept the reality of the world with which we're presented. It's as simple as that.